Cool. We should be able to see. There's my dot cam. So we're going to get going. I just want to jump right in today. And again, if any issues come up, let me know that we can hear, see. If you have questions on material, most definitely, right? So the curve sketching, that question I gave you for that quiz, I've seen a lot of your emails. I haven't had a chance to respond that I've received them, and I still have to grade them this week, of course. I've been seeing them come in. I know that one was a little bit tricky in terms of having that exponential function involved, okay? But hopefully the work with the derivative, second derivative involving looking for where we're increasing, decreasing, not too bad. All right, so now we're going to jump forward though. 4.6 is kind of working with the calculator for that curve sketching. All right, so let's jump into 4.7, which is our optimization. Okay, and so for our optimization, try to get this to focus and be a little bit clearer to see for everybody. Not too much jostling around. All right, so here's our word problem section of this chapter. Okay, our optimization, our applications of the derivative, right? And so exactly when we're optimizing, we want to optimize a function and equation, right? That means we want to find where a maximum or minimum will occur, right? So for example here, items that we want to optimize, right? Maybe we want to maximize the profit for renting rooms at a hotel. I know with the pandemic, right, that example might seem a little bit off because not many people are traveling, right? But this idea, like if we're running a business, you're trying to maximize your profit, okay? So exactly that. When we're optimizing, we're trying to maximize some quantity, right? Or exactly here, well, maybe we'll start off with a lot of our problems geometric. Maybe we want to minimize the amount of material used for packaging, right? Again, especially nowadays with our concern for the environment and whatnot, right? We want to kind of reduce our impact. So we try to use as least materials as possible. So maybe we're going to minimize the material used for packaging. And so just a side note, just kind of get us thinking in this context, what that's going to look like, what we'll deal with, right? Maybe we're going to want to minimize surface area, right? So a lot of our work we start off with is probably going to be geometric, but then we can also deal into more, you know, natural sciences, business, other applications. Okay, I know there's a question that I received before about kind of doing some maximizing, getting the most profit and whatnot, looking at these equations and so on. And so our big work here, when we start to optimize a function and equation, when we go through these applications, right, our kind of important aspect is going to be here. We need to find an equation or a function that can depend on a variable that will allow us to differentiate and determine these locations, these values for maximums and minimums. All right, so in some degree similar to our related rates, right? Trying to get this equation that's going to relate these two quantities, right? How much money we're making with how many rooms we're renting. Okay, here relating, right, what we're trying to package, a certain volume that we're trying to contain, like thinking like soda cans or something like that. We have a certain volume that we want to enclose, right? And then the surface area, those dimensions of the packaging we're going to use. So finding variables and whatnot to relate those quantities. And then we're going to look through our work in section 4.3, right? Differentiating, using that first derivative or even second derivative test to determine those max and mins, where that's going to happen. So a big part of it, though, is getting that variable, though, what it represents for us, that x, that t, whatever it might be. So we understand, okay, this is the quantity we're going to use to get that biggest, that maximum, that minimum, that smallest value we are identifying, okay? And so, of course, as we start off with, like we did with related rates, is probably going to be some geometric problems first, and then we'll dive into more kind of real life and science applications elsewhere, okay? All right, but in this optimization, we're trying to find where these max and mins occur. So definitely it's going to be a lot of work in section 4.1 and 4.3, looking for those absolute maximum minimums on a closed interval, looking for where those max and mins occur based on where our derivatives increasing, decreasing, so on. All right, so with that said, let's jump into an example. So for our first example, and again, I know I always tell this story in my classes, this is the example, the problem I had gone through when I was getting hired for this job initially, okay, however many years ago, right? Unfortunately now, especially because of our situation online, I can't really bring in the big physical kind of example, but at least we can work the problem. All right, so for this example, let's say here that we want to create, okay, we want to construct a box, this rectangular prism in 3 dimensions, okay, without a lid, using a square piece of cardboard. And I'll have to slide this up in just a second, okay? All right. So we're gonna construct this box, this rectangular prism, without a lid, okay, using a square piece of cardboard with side length 3 feet. Okay. So 1 yard, 3 feet across the side, 3 feet across the top. We'll draw that picture in just a second. Okay. And then again, how we're going to do it, we will cut a square from each corner to remove so that the remaining sides can be folded up to create the box. Again, I know it's kind of long-winded here. It's a square here, sorry. All right, so here's our question. How large of a square should be cut to maximize, right, to get the greatest possible, what's the greatest possible one inside the parentheses there? The greatest possible the volume. I know that is going to read a little bit awkward. Sorry about that. Right, we want to maximize the volume, right, to get the greatest possible volume. There we go. Okay, of that box constructed. All right. I know it's a long paragraph there, but hopefully there. Okay. Yeah, I know it's a lot to write, so I'll give you guys a moment. All right. So let's start to think about and draw this information, right? So we're gonna make this box from a piece of cardboard, side length 3 feet. Okay. So in this case, if we have our piece of cardboard here, okay, there's our cardboard, where we have this measurement from edge to edge, 3 feet. Okay. So there's that part. And then what we're gonna do, we're gonna cut a square the same size from each of our 4 corners. Okay. And so once we do that, what's going to happen with what components we have remaining, we're going to have this box left, right, where the squares we cut kind of create that height. As best I can try to draw this three-dimensionally and try to color coordinate. Okay. All right. Not too shabby. All right, I know it's not a square. It should be a square there, but there's our box. Okay. So here's the box. Here's our cardboard we're starting with. Okay. And so we're trying to figure out how much do I cut. Okay, and you can imagine, let me even just borrow, here, let me grab a color sheet of paper, I'll be right back. All right. There we go, okay, so back, hopefully you still hear me, good. Imagine there, all right, so here's our piece of cardboard, right? And we're gonna start to chop off a corner. Okay, there's one corner. Do my best to keep it roughly the same. 2 corners, 3 corners. All right, so 4 corners. Okay, so you can see as best I could. Not that you need to see the trash, but there's my 4 corners, okay, that I've chopped off of my square cardboard, okay? And so here, doing that, now, there we go, cool. Once I get that cut out, then we're gonna start to fold up our different sides. So it's along those edges, boom. I know, again, maybe a little bit laborious here, but just so we can kind of visualize. So now, I'm not sure how well that hot pink shows up, but now we have this box, okay, constructed, okay? And so depending on how big we make those squares, right, how much we cut out, sorry, bobbling around here, how much we choose to remove from those 4 corners, right? We can take out bigger chunks from those four corners, fold that up, and now have another box. And so we're trying to compare between these two, right? Depending on how much we cut, which one, or multiple, right? We can start to get to fractions of inches and everything else down here, but which is going to have the biggest volume that we can enclose? Okay, is it better to be shallow but wide, or is it better to be tall but a smaller base? What's going to be best, right? If we maintain this shape. Okay. So again, that's the big part. Again, just like related rate, drawing a picture, visualizing what it is we're building, we're doing, what we're trying to maximize, so on, can be a good assistance, right? All right, so there we go. So now let's start to look at it. So we're going to have this box, and we're going to start to cut out a portion from each side. And again, it's going to be a square, so it's going to be the same width on either side. So what do you want to call it? W for the width of that square, or X? Each one is going to be identical. So that's what we're going to cut out. Okay, or I probably should have called it X, because now when I get to this part, as I started to cut that out, right? Once I cut out that width, that X, I probably should have more realistically called it. Once I cut that, that becomes, when I fold up, right? That becomes the height for that box, right? So over here I can relate, and again, that's probably why I color coded. We get that piece, that W, that's going to be our height for that box. Okay? So I can start to import, I can start to identify there. And so now let's get back to our problem. What do we want to do? We want to see here, how can we maximize the volume? That's what we want to keep track of. What is it we're optimizing? Right? We want to maximize the volume of the box. So for that box, what's the volume going to be, right? So our volume for a rectangular box, length times width times height, right? And this is where I kind of messed up, because I called the height of the box W, so it's going to look kind of weird, but let's get to it. Right, so this is our equation. That's our relationship. We're trying to maximize that volume. For what values of length, width, height are we going to get the biggest possible volume? Right, and so as before, we don't want so many variables, right? When we're taking a derivative, when we're looking for that maximum, our discussion here, we only want that volume, that quantity we're trying to maximize, to depend on one variable. Okay, I'm going to zoom in. It might be a little bit small to read. Okay. Okay, and I don't know, for myself, I kind of see that little drawback, that relationship back to related rates, where we did want to get things in terms of one variable, so on. Okay. So hopefully we're not too traumatized by the related rates discussion, that this seems okay. Okay. All right. So now with that said, let's start to bring back this diagram. Okay. And we'll start to work on that. So again, depending on your variable, whether you call it X, I absentmindedly call it W for the width of for that square, but that's all right. And now this comes up with another statement. When we're doing this process, again, watch your units, right? We're dealing with feet here. We could just as easily convert these to inches. 36 inches, right, for 3 feet. 1 foot's 12 inches. So if we wanted to, we could also call this 36 inches. Either way. So just keep track when we start to compute and get our solution. we understand what our result, that answer, is kind of representing, and also how it's being measured. Okay, so when we're talking about time, are we talking about time in terms of minutes, hours, days, that kind of idea? All right, so now with that said, redrawing this picture, cutting that out, WW, right? Boom. And again, I know maybe a little redundant here, but let's go here. Okay, so once I make that cut, we can talk, we've talked about already how that portion becomes that height piece, right? So that W, let me finish drawing this so I don't get it too messy here. All right, I'm not spending all my time drawing here, right? So that's going to be our height piece of it. All right. Getting back to it, sorry guys. Okay, there we go. Quit doing dilly-dallying with that. So we have our height. So we have that piece of it. But now let's think about that length, and I'll call it width here, length and width. Okay, there we go. So in these cases, the length and width, right, are going to come directly from how we're folding up that cardboard, right? Because this side was X. Is that visible? I know it's a little bit light on my end, right? There's X and X, X and X, right? So we're going to cut out those sides. And so what's left over when I have it, this full space was that 3 feet or 36 inches. But now we're chopping off the X up top, X down below. So then this space in between, 3 feet minus the 2X. Okay, so in this region here, that's the 3 feet minus 2, oh sorry, W, I call this. Okay, and then similar on this side, right? 3 minus 2 W. So let's see. Okay, so let me set this up and let's have you fill in, okay? I'll be right back here in just a minute. Let you. Oh, sorry about that. So let's see here. So now, building that up, okay? So for our length, that component here, 3 minus 2W. The width, since we're dealing with a square piece of cardboard, right? You can imagine if we had a rectangular piece of cardboard, how we have to alter, right? If this was instead like 6 feet wide by 3 feet high, so on. Those differences would be altered accordingly. And then we're going to multiply it by the height, which I had called that W, right? But again, how you use X, you could do it that way. S for the square, whatever it is. So now we have this new equation, this new formula for the volume of that box in just one variable. Okay, so now as we start to go through, expanding this out, foiling, distributing, whatever you want to call it. 3 times 3 is 9, minus 6W, minus 6W, plus 4W squared. That's still going to get multiplied by W, and we'll combine like terms. So in the end of the day, what do we get? We get our volume, 9W minus 12W with another W, so minus 12W. squared plus 4w cubed. And we can rearrange, put this in descending order, like so. Boom, boom, boom. Okay. And again, any of those steps unclear, let me know. But there's our work and just getting the equation. So I haven't done any calculus quite yet, just like our related rates. There's one step of calculus really. The maximum for this function, for that equation. Okay, so that's going back to our 4.3, 4.1 discussion. Given some equation, some function, can we find the max or min? Okay, critical numbers, first derivative test, all that fun stuff. Okay, all right, so with that said, taking that derivative with respect to w, right, the volume depends on the width, the height, right, that component we've taken for our square. So taking our derivative, v prime, 12w squared minus 24w plus 9. Our critical numbers where that derivative equals 0. Okay, so our critical numbers where our possible maximums can occur. All right, v prime equals to 0. So solving your 12w squared minus 24w plus 9 equals 0. Factoring out here a 3.
Remember our deal? What happened? What happened? What is it? This is what you do. What happened?
4w squared minus 8w plus 3 equals 0.
Go sit down, Jennifer. Go sit down.
Factoring here, that should factor.
I'll be right back,
Okay. So factoring here, if I remember correctly, we should get 2w to get the 4w squared. Right, negative 6 minus 1 or minus 2, negative 8 plus 3. Okay. And then separating that.
We need to play together. Remember our deal? Play together.
Solving here, adding the 1, dividing by 2, w equals 1/2. One more time here, w equals 3/2. So now we have these two options where max or min can occur. Okay, and we'll come back to those pieces, but just going into that mode of our first derivative test, we had these two critical numbers. Where our derivative equals 0. Choosing some values around it. 0, 1, 2. And I'm going to plug into that factor form. Just a little bit easier to evaluate. That 3 out front isn't going to affect our sign. It's positive, right? So really it's these two factors, sorry, that are going to play a role. So with w equals 0, plugging that in, 0 minus 1, negative, 0 minus 3, negative, negative times negative, we're going to get positive. Right, so we're increasing here. At 1, And again, having to calculate out, that's perfectly fine. 2 times 1, 2 minus 1, that's positive. 2 times 1, 2 minus 3, negative. Positive times negative, negative, right? So we're negative here, decrease, right? So right there, even with our first derivative test at that 1/2, climbing to that maximum, right? So that's just for good measure. See what's happening over at 2. Two times 2 is 4, minus 1, positive 3. 2 times 2, 4, minus 3, 1, still positive, positive on this side. So in that case, there's going to be a minimum occurring there. We're focused on where we're going to maximize that volume, right? So we're looking for, in this case, right, that maximum, right? Minimum, we don't want. Right, and so there's our first derivative test to double check. So going back in that context, right, going back to it, a maximum for the volume occurs when W, right, the width for the square, we cut out, is 1/2. Let me maybe color code that red here, right? But now think back to our units, right? We were talking about before. In this context, if I was using that 3 minus 2W, right? That 3 was in feet. So that's exactly what that's going to be, right? So we get 3 feet or 1/2 foot, 6 inches, okay? Right. When that W is 1/2 foot or 6 inches there, okay? So that idea, going back to our image, that if I was to cut 1/2 foot, or I'm going to go into inches for a second, six inches on both sides, okay? In total, it was 36 inches, right? Same thing for the other dimension. If we need to see this, we can, okay? What's remaining here? 36 minus 12, or 24 inches for that width, right? So for our component here, we're gonna get this box with a base, a square of 24 inches, and the height 6 inches as our greatest volume. If you want to calculate the volume, of course, you can do that. I know all my time spent on drawing this thing out, but just trying to get that visualization. Okay. And so we can get the dimensions. We can get the volume to actually calculate it to compare. Okay. And so this is where I kind of discuss also that idea of using 4.1's tactics of looking about finding a max and min on a closed interval, right? So I'm going to take a moment here, take that away for a second. Hopefully that discussion is clear, right? But now here, in the context, in the view of section 4.1, that max, min on a closed interval right? Let's think about that value for W, right? W, that stood for that width of the square to be cut, right? So when we start to look at that right up here, well, the smallest W could be is 0, right? 0 feet, 0 inches, right? Basically, we do not cut anything. But in that case, if we don't cut anything, then it's just a sheet of paper. We're not going to be able to fold anything. It's not going to be a true box, right? So it's not going to hold any volume. That's going to be a volume equal to 0 here. Right? But now what about the biggest? What about that? Right, so that's where we have to think about, okay, whether we do it in feet or in inches, right? As we start to cut out, right? 0, nothing, right? 16 is where we're going to be the best. We can cut out more, maybe we cut out 8 inches, 12 inches from both sides, right? But again, we have to think about, we're cutting the same amount on both sides, or all 4 sides, really. So at some point, right, I can't cut 36 inches because I'll cut all the way across. There's nothing for me to cut this way. And vice versa, I can't cut too much because then I'd be cutting too much from one side. I won't have the same amount on both, right? So since we're cutting equal amounts, right, on either side of that 36 inches, that 3 feet, right? The most we can cut on either side physically, okay, how deep I can make that cut, right, would be that W is going to be 18 inches, right, or 3/2 of a foot, right? Because once I get to 18, right, cutting that mark in the middle, let me go this way, 18 on both sides is going to be in the middle. But again, that's going to be that kind of similar idea of not cutting anything, because if I cut it all the way across, it's basically what's happening. If I cut it all the way to the middle, cut it to the middle, halfway, it just shaves off that complete size. So now I'm just at a loss. I don't have anything to fold up. And imagine doing it this way. What it's going to do is compacting down to a point. You're not going to get anything. This is going to be another situation where your volume equals 0. Okay. So going back to our number line here and thinking about these values, right? It makes sense that we're getting this minimum at 3/2 because that's the case when we're cutting so much from either side that there's truly no real box left over. Everything's being stripped down, so you're not getting anything. You're not getting any volume there at all. Okay, and so kind of going back to this, what we'd actually kind of inspect then is that we would create this closed number line where the smallest we can do is 0, the biggest we can do is 3/2 or that 18 inches. Sorry, there's my value for W. And then we had that critical number at 1/2 inside that space, right? So again, when we start to do these problems, like we did back in 4.1, when we start to look at these critical numbers, possibly in the back of our mind, we're thinking back to, okay, in the real life context of the problem, if we have multiple critical numbers, is it going to fit in that relationship, right? We can do it that way. But also, once we start to look into our number line, our first derivative test, where we're increasing, decreasing, that should always, hopefully, fingers crossed, clearly inform us where that max and min show up, okay? The only hesitation, the only trouble comes in, again, going back to that 4.1, is that we're going to want to make sure we do check those endpoints, right? But most often, right, 95% of the time, it's going to be whatever critical number shows up in our calculation. Every now and again, geometrically and otherwise, we can think about those endpoints, okay? Of what our variable represents first and what it could possibly grow as large as or be as small, so that we're not including negatives, right? I can't take a negative dimension. I can't take negative 5 inches off of that box. I'm not adding to it, right? And again, I can't cut more than what is already present, right? If I have this board and I'm trying to do something with it, I can't, have a board at 6 feet, but I need 8 feet of wood to do something. It just doesn't work, okay? So just kind of bringing in those context, that understanding physically of what these values represent for us and what to do from there, okay? All right. Good. So that's kind of a good example to start with. And not much time as our first example runs a little bit long to discuss and describe. Okay. And so for the plan for the rest of the week is just to kind of maybe do another one of these, but then really jump into chapter 5 to see that work. The last major topic for this course. I know we're running short on time. For our final exam is going to be similar to our chapter 3 exam, right? I'll put something on Canvas for you guys to work on, a little bit of work from all the chapters we've addressed, okay? And we'll talk about what to do for chapter 5, okay? It's not going to necessarily be heavily weighted on chapter 4 alone. I just want to make sure, right? Because again, we're still advancing to 20B, our next semester calculus. So making sure we can do some limits, definitely a lot of derivatives, okay? And then just some of these applications we see, we'll talk about, okay? But definitely as we go through the rest of this week, maybe another optimization problem for tomorrow, but definitely wanting to get into chapter 5. I might start just kind of scanning and send you guys some notes that I had before to kind of lay the foundation, to lay some of the work for our chapter 5 discussion and integration, so we can really get into the business of doing that work in our Zoom meetings, okay? And then the final exam, like I said, is going to be the following week, okay? Next week, Tuesday, Wednesday, I'll probably have it open for you guys to work on, very similar to what we had done for our chapter 3 exam previously, okay? All right, so as we get closer, right, throughout the rest of the week, I'll keep on discussing what we're gonna expect and do manage for that final, but just to get you guys aware and ready, all right? So again, no exam for the chapter 4 stuff. We're just gonna kind of bank on preparing for that final and have it do it that way, okay? Again, I know I still have to scan those exams. I've been hesitating on doing that with my phone, okay? Needing to get on campus to do that. But I will get those chapter 3 exams to you this week for your review, for questions there, and also the related race quiz. I set the grade, and then there's one you just turned in, okay? All right, crew, so that's it for me today. Thank you very much. All right, if you have questions, of course, email me, stick around, let me know. But hopefully this discussion, let me box in, this is our answer. For that optimization problem. All right, crew. All right, that's it for me. If you have questions, stick around. Email me, use the chat, whatever it might be. Otherwise, there we are. Very good. Thank you very much.